Hello guys, in this video we will be seeing a step-by-step example of the Kruskal's algorithm. Now, let me explain very briefly what this algorithm is about. We use Kruskal's algorithm to find the minimum spanning tree of a graph. In summary, we're going to start with a graph with the following characteristics. It is connected, weighted, and it is an undirected graph. In other words, there is a connection between all the vertices. This means no single nodes. All the edges have weights, meaning that there is a specified distance between all the nodes. And finally, there are no senses on the edges. You can, for example, go from B to C or from C to B because there are no arrows on the edges indicating a specific orientation. If we apply the algorithm to a graph with those characteristics, such as the one that we see down here, we will find the minimum spanning tree, which is going to have the minimum possible total edge weight. In other words, when we add up all the weights of the edges, this number is going to be the minimum possible. Also, it is going to have all the edges connected. In addition, because it is a tree, it is not going to have any cycles. And finally, the edges of our spanning tree are going to be a subset of the edges of the graph. So it will contain less edges than the graph. Okay, now that we know the characteristics of a minimum spanning tree, let's do the following example to show how the algorithm works. The graph that we have here has 9 vertices, and all the edges have a marked weight. As we see, to go from A to B, or vice versa, we have to go through 4 units. Before we start, we are also interested in knowing when we are going to stop. The stopping condition of this algorithm is when the number of edges that make up our minimum spanning tree is equal to the number of vertices minus 1. In this case, it's going to be 8. When we find that the spanning tree has already 8 edges, we stop. Okay, so the first thing that we are going to do is to list all the edges that we have in the graph from lower to higher weight. We see that, for example, we have one edge with 1 unit. It's right here. 2 edges with 2 units. Those are right here, CI and FG, and so on. We put the edge with its corresponding weight in this table. Also, for this example, we will analyze the vertices alphabetically. So if we find a tie and we are not sure which one to select, because 2 or more edges have the same weight, we will break the tie analyzing first the one with a higher priority alphabetically. For example, in the previous case, we put CI first than FG, because C comes first than F in the alphabet. Of course, you can find other examples out there where they do not include this condition, but they still come up with a minimum spanning tree. In this opportunity, to make a simple and clear study case, I have decided to break ties alphabetically. Now, we're going to begin to choose the edges from the top of the table to the bottom. Again, as we said before, from lower to higher weight, which will be forming our minimum spanning tree. Moreover, we are interested in the edges that do not form a cycle in the spanning tree. If an edge creates a cycle, we just discard it. A cycle in our original graph is, for example, the one composed by A, B, and H, with their edges 4, 11, and 7. We start with the edge HG with a weight of 1 because it has the lowest weight. The following 2 edges are CI and FG. Both of them do not create cycles in our tree, so we include them. We can also see here to the right how our minimum spanning tree is growing. Because there are no edges with a weight of 3, we continue with the ones which have a weight of 4. We can add AB, no cycles formed, and then CF. Up to this point, our spanning tree has 5 edges. Here we have an interesting situation with GI. If we add this edge, we form a cycle between vertices C I, G, F, and C again. So we have to ignore this edge. Now edges with a weight of 7. We have AH, we can add it to the tree. CD, the same case. But here, if we add HI, here, we create a cycle with C, I, H, G, F, and C. This will be our cycle. So we can't add it. We see that the spanning tree has 7 edges so far. So we only need one more until we reach the stopping condition. Okay, BC can be added because we will have a cycle in B, A, H, G, F, C, and B again. This will be our cycle, so we have to ignore this edge. Finally, we can add DE with no problems. And we stop right here because our tree has 8 edges. Remember, this number came from the number of vertices of the graph minus 1. We also see that we have all the vertices of the graph included in the tree with no cycles. Okay, so here it is, the minimum spanning tree we have found. To know the total weight of this tree, we can simply add the weights of all its edges, and the result will be the minimum value that we can find from the original graph, and complying with the characteristics that we mentioned at the beginning of the video. Thanks for watching, and stay tuned for other videos.